We're trying to show that the measure, the cosine of the measure of an angle in radians is irrational, okay? And let's start with just a basic fact. Some of you may not enjoy working with radians, but pi radians is equal to 180 degrees. And if you just look at the definition of a radian, it's a big wordy definition, but it's exactly that angle, precisely that angle that has an arc length that's equal to the radius of the circle, okay? And this really is more natural to say 2 pi radians is equal to 360, and that just follows immediately from the definition of a radian, okay? Now, so we know that pi rads is 180 degrees, and that means that pi over 9, okay, this would be the same thing as cosine of 20 degrees if you insist on the degree measure, okay? So we want to show that's irrational. You know, that means we're trying to show that this is not equal to the ratio of 2 integers, and I'll call those integers to be a and b, okay? And y'all, etymologically, irrational means not a ratio. Doesn't mean somebody's crazy. It means this is not a ratio. Ir negates ratio, so it's not a ratio, and that's that's the meaning of it. Okay, so now, not too surprisingly, we're going to use this triple angle identity, if you want to call it that. And some of you who've sat through a trig class have seen this before, and it's proved usually using the double angle formula in various forms of the Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. But I want to show you a way, or at least the start of a way, that's a lot nicer, in my humble opinion. If you've heard of D'Moivres Theorem, French name, Moivre, I think, but cosine x plus I sine x, whereas the imaginary value square root of -1, like this, okay? Now we'll use 3, but it holds in general for any natural number. We'll put 3 here. Okay, this is kind of cool, and it's based actually on trig why this is true. You know, the addition and sum and formulas for sine and cosine come up when you're actually proving this in an inductive sort of way. But this is actually equal to, the 3 comes inside. You know, it's the base. It's why it's so easy to multiply and add complex numbers, really, or do arithmetic with complex numbers. So this is cosine 3x. God damn it. This is cosine 3x plus I sine 3x. Okay. And I'm not going to do the proof, but the proof follows in not too many steps from this, just by equating the real and the imaginary parts. So you can use this to actually prove this statement for all real numbers, okay? Again, that's a separate exercise if you feel like doing it, okay? Now we're going to pick these assignments because cosine of pi over 3 is a rational number, okay? So if we make this assignment, and I didn't write down that x will be pi over 3. Okay, and you again retrospectively you can look at this and see why this is important, because with these assignments this becomes this, right? So you see, this would be the cosine of 1/2 right here. When you bring it to the other side and multiply by 2, you end up with this third degree polynomial. Okay, a third degree polynomial, where, by the way, all the roots sum up to 0, which, you know, it doesn't make any difference by the Vieta's results. It doesn't really relate to this that much, so it was kind of an unsolicited comment there. But so we're wondering about the solutions to this, because y is equal to cosine of pi over 9, and let's not forget, we're trying to determine whether or not that's irrational or not. We're trying to show that it's irrational. Now, another very well-known result, the possible zeros right here would be y is equal, you list, the only divisor of 1 is 1 and -1. So you can do this. You can do plus or minus 1 over all of the divisors of 8, okay? Well, that would be 8 itself, plus or minus 1 over 4. 4 is a divisor of 8, plus or minus 1 over 2, and finally plus or minus 1. All right. Now, so there's 4 numbers here, but each of them are plus or minus, so there's 8 solutions. I'm just going to come out and say you can check them if you want, but I checked them and there are no solutions. Okay, long division is probably the easiest way if you want to do it by hand. And y'all, again, maybe I was too hasty in the statement of the rational zero theorem, but what it says, if this polynomial has rational solutions, it has to come from this list, which are the divisors of the constant term in the numerator over the divisors of the leading coefficient in the denominator. That's essentially the verbose version of the rational zero theorem. So there's no solutions, ergo y, I'll just say it right here, y is not equal to a over b. And this is literally directly, and that's for any possible integer. This is impossible, and that means that this is irrational, right? So this part right here would be QED. Okay, so we proved it. I thought it was kind of nice because even though I didn't see it to the finish, this D'Moivres theorem, I never knew. In trig, you learn how to do this, like I said, by the double angle identity and then these various rearrangements of the Pythagorean identity. Okay, and you can get it done, but this turns out, go ahead and do this out and you work with this and see if you can see. In my opinion, the proof when you start from here is much easier because you see how cosine of 3x just pops out. Okay, and the real part, this will be the real part, and then you'll get the real part of this and equate it, done. Okay, it's kind of cool, you know. So anyway, it's what they call a more elegant proof than just just hacking through it from a pure trigonometric perspective without D'Moivres theorem. Okay, that's all. Thank you for viewing.